Let's look at timing checks. In this module, let's identify what the setup and hold checks imply, how it affects the flops, and how information is stored in the flops. Then we will identify how they are stored in the libraries for the STA tools to use. A flop or flip-flop or register, as it is commonly known, is one of the common storage elements, and it is edge-triggered. If we look at the timing arcs in the flop, you have the D to Q timing arc and then you also have the clock to Q timing arc. One thing to remember is that in an edge-triggered flop, the input data is propagated to the output only when the clock triggers the data to go from D to Q output. So, all the timing information that is calculated is from that clock edge. When you look at the timing calculations, the clock to Q delay of the clock to Q timing arc is what is used in timing. STA tools will use that clock to Q delay. Whenever you look at timing reports, the delays are calculated from the clock edge. So the important timing parameters in a flop are the clock to Q delay. We also have setup and hold time requirements. We'll talk about those in a second. For the data to be safely stored inside a flop, the data must be stable for it to trigger the saving of the data into the flop. If the data is not stable and changes during the setup time, the data is not stored in the flop. If you look at the graphic below, there is some slow logic, and the data is going from Q1 to D2. The data is being transferred from FF1 to FF2. If you look at the D2 signal, the D2 signal is changing before the cycle 2 of the clock starts. The new data is ready to be saved into FF2 at the rising edge of clock cycle 2. But, the D2 signal just changed value right before the clock edge without meeting the setup time requirement. Therefore, the data will not be stored into FF2. The reason for this is the slow logic. Obviously, Q1 and D2 are different signals and even though they have similar waveforms, there is a delay between them. The Q1 signal takes some time through the slow logic to arrive at D2. Q1 data from the previous cycle changed before the cycle 2 begins because the rising edge for clock in cycle 1 triggered new data into FF1, thus changing Q1. And now the new data is already at Q1. The old data barely arrived at D2 and was not yet saved into the target flop FF2 before changing into the new data. Thus, by not meeting the setup time of the flop, it caused a setup violation. Therefore, setup time can be defined as the duration of time that the input data must be stable before the triggering edge of the clock. Setup violations can be remedied by either slowing down the clock by increasing the period or by decreasing the delay of the data path or slow logic. A positive edge triggered D flop stores and holds the old data until the next positive edge of the clock arrives. In this case, you have two flops with the data launching from the FF1 flop and captured by the FF2 flop. At this point, in FF2 target flop, when the data from the previous cycle arrives at D2, it can enter the flop even though the clock is low but is not fully stored because of the delay inside the flop and it waits for the rising edge to store the data inside the flop. What happens when D2 is slow to arrive? If the data from the FF1 flop takes too long to get to FF2, then by the time FF2 is ready to store the data from the previous cycle, the data starts changing into the new data from the current cycle. Because the new data possibly conflicts with the not fully stored old data, it creates a race condition between the old data already inside the flop that is not yet fully stored and the new data just arriving at its input, and therefore the stored output of the capture flop is unknown. Therefore, when your data is slow to arrive and the setup time is violated, the new data is considered lost or unknown. To avoid that situation, the data must arrive in time for the minimum setup check must be met and for the data to be properly stored in capture flop. When you have a really fast clock or when you speed up your clock, your setup time is violated because now the data becomes slower compared to your clock. The new data is actually lost. For good functioning circuitry, your clock cannot be too fast compared to your data. In order for your data to be safely stored, the other requirement is your hold time. The hold time is the duration that the D input must be stable after the triggering edge of the clock. So the data must be stable. The data delay must be greater than the hold time of the target flop plus any clock uncertainty between the flops. This means that your data cannot be too fast compared to the clock. You can correct the hold violations by providing some data delay. You can either decrease your clock uncertainty in the design, or you can also add delay cells. You can reduce the amount of skew between the clock trees by using better clock tree generation. If you constrain your clock trees properly, there won't be any hold violations because that minimum data delay requirement is now met. If we look at this illustration, the D2 input is switching when the old data is being captured into the second flop. Therefore, the data is not captured safely into the new flop. What happens when the data changes immediately? You'll have a hold time violation. And even though it is caught within the edge, the data is still lost because the flop didn't even fully absorb the previous data into the flop before the data changed a second time. For the data to be safely stored into the flop, the new data must not arrive so fast that the flop doesn't even absorb the data from the previous cycle. Therefore, the hold checks are done at the same edge as the launch edge, rather than doing it at the capture edge like in the case of a setup check. If the data doesn't change faster than the hold check, then it most likely will be safely captured into the flop, unless there is a huge skew between the flops. This is why it is important to invest effort into building well-balanced clock trees. The setup and hold checks are stored in your libraries, the .libs, in the form of a lookup table. The lookup table contains the setup and hold values that are calibrated at several values of load and skew for each of the flops. The setup is shown as a positive value. The signal timing to the flop has to meet or exceed that setup value, which is done as a check at the capture flop during timing analysis. For the hold, the values are shown as a negative value. Both setup and hold have to be met for any particular capture flop to safely save the data into the flop. Take a minute to try this activity. When you have multiple clocks in the design, look at the capture clock and the capture flop during your setup checks. Even though there is CLK1 and CLK2, CLK2 is the one that determines the safe storage of the data into the F2 here. Make sure that when the setup checks are run, the setup check is happening on F2 and not F1, because there are different edges where the launch and capture can happen. In the case of multiple clock domains, we do need to look at the most restrictive capture and launch combination. If we look at the time 0 launch, the capture will occur at the trailing 3. Whereas if we look at the leading edge 8 launch, the capture will happen on CLK2 at the trailing 9. This seems to be the most restrictive or worst case combination. We have to look at that worst case combination of launch and capture to make sure that the design meets the timing or the setup check for that particular restrictive capture and launch combination. The hold check is a little more complicated. We have to understand that whatever edge is launching the data, if the next edge is not launching the data again before the previous one is saved, then you're okay. So, if you launch at 0 and at the trailing edge of 3, if the data has not completed saving into the F2, then you don't want the new launch at 4 to give you new data. You would want it to wait until the data is safely stored. If we look at the launch 4, the trailing edge at T3 still hasn't completed saving. That is necessarily the most restrictive edge, and therefore the hold requirement is done at T3 for the hold check. So, if we look at the most restrictive launch to capture its 4 and 3, and the data is safely stored, then you're okay. Otherwise, you're failing the hold check. In timing reports, some tools report the difference in the most restrictive launch and capture edges as phase shift. This can be helpful in calculating the time required for the data to arrive at the capture flop. Phase shift is a concept that helps create better timing reports when you have separate clocks for launch and capture. But, even in case of using the same clock for both launch and capture as shown in this example here, some tools separately report a phase shift of 1 clock period and then including the phase shift of 1 clock period in the required time calculation for setup. For multiple clocks, we must understand the basics of phase shift. Let's look at how phase shift works. Phase shift is based on ideal clock edges and not on the real signal edges. First, identify the launch clock and capture clocks. Then start your timing analysis at time 0. Identify the worst-case launch and capture after unrolling the clocks. Most likely these most restrictive launch and capture edges are not in the first cycle. But you can visualize that worst-case scenario like it happens in the very first clock cycle by shifting the capture clock until the same restrictive transfer also happens in the first cycle. Then you record the amount of shifting you did to the capture clock as phase shift. Thus, phase shift can also be defined as the delay adjustment used so that the first clock cycle edges represent the most restrictive timing edges. For setup or late phase shift, the capture edge occurs after the launch edge, and so we must unroll the ideal clocks, try to find out what the most restrictive non-zero delta is, then shift it to the first cycle. Whereas with the hold, the capture edge happens before or equal to the launch edge, but the same unrolling happens, and we must figure out what the most restrictive non-zero delta is, then we shift it to the first cycle. There is a simple equation that works to calculate phase shift for both setup and hold. The way it works is to identify the most restrictive launch and capture edges. Then identify the first capture and launch edges from your first cycle. Once you know those 4 edges, you plug the time units at which they occur into the equation CE minus LA minus C1 minus L1, and this will give you your phase shift value. Let's look at an example of phase shift calculation for setup in a multiple clock domain scenario. If we unroll a 4 nanoseconds clock and a 3 nanoseconds clock, the LCM least common multiple is 12. For a negative edge triggered flop, what we're doing instead of using the CLK2 is we are reversing the phase of CLK2. Notice that the leading edge of CLK2 is a falling edge. Looking at ideal clocks here, we align leading edge to leading edge after unrolling. Then we can find and determine that the most restrictive non-zero delta would be at 8 launch and 9 capture. In the first clock cycle, if you choose the launch edge at 0, then the first trailing edge at 3 nanoseconds is the capture edge. This has a difference of 3 nanoseconds. Notice that the launch edge is a leading edge and a rising edge of CLK1. Notice that the capture edge is a trailing edge and a rising edge of capture clock CLK2. If you choose a launch edge of 8 nanoseconds from the launch clock CLK1, then, choose the capture at 9 nanoseconds. This is the most restrictive launch to capture because the launch to capture has the smallest difference of 1 nanosecond. If you want, go ahead and verify all other launch to capture scenarios to confirm this conclusion. Let's pretend that this same scenario is happening in the first clock cycle. To do this, move the capture clock waveform so that the most restrictive scenario happens in the first clock cycle. In this case, we can move the CLK2 waveform to the left by 2 units and we can see the most restrictive scenario is in the first clock cycle. These 2 units are considered phase shift because we are moving the waveform by 2 units. So, if you arrive at the phase shift via calculation, it is also the same value of -2. Therefore, this -2 nanoseconds is the value for phase shift for setup. In this multi-clock scenario example, we have the 4 nanoseconds and 3 nanoseconds clocks for the launch and capture. In this case, after unrolling the clocks, the most restrictive non-zero delta is shown at 4 nanoseconds launch and 3 nanoseconds capture. And for the first clock cycle, for a launch at 0, the capture is also at 3. Thus, the phase shift is calculated as -4 nanoseconds. And this value of -4 nanoseconds is used as a phase shift in the timing reports. Try this activity to improve your understanding of the topics discussed.